Hey science nerds, my name is Bill and I'm a PhD candidate at UCSD. I'm here in my kitchen to answer a question from Heidi of Tijuana. So before I answer this question, I'm going to try to put it in context. So when you open a can of soda, there's two states of matter involved. There's liquid and there's gas. And so when you open the can, you're releasing pressure that is keeping the gas dissolved in the liquid. Bubbles form in the liquid and then they rise to the top because they're less dense than the liquid. And the only reason that they don't burst immediately when they get to the top is that a thin liquid layer is formed between that pocket of gas and the air in the room around you. So if that pure liquid layer is water, then the bubbles burst very quickly. Here, I'll show you some pure water with carbon dioxide gas dissolved. So you can see there's bubbles forming, but for the most part, they break once they get to the top. And the very surface of the liquid there's not very many bubbles there. So that's pure water. On the other hand, when there are carbohydrates and proteins dissolved into the liquid along with the gas, then there's a stronger, more stable, thin liquid layer that's keeping the gas and the bubble separated from the air in the room. So this is a liquid with carbohydrates, proteins, and again, dissolved carbon dioxide. So now you can see the bubbles stay around a lot longer, and there's a big thick foam. That's because the bubbles are more stable, because it's not pure water. And the same thing happens regardless of whether the gas is carbon dioxide or some other gas, for example, nitrogen. So this is, again, liquid with carbohydrates, proteins, and a dissolved gas, but the gas is nitrogen instead of carbon dioxide. So again, you can see some very stable bubbles. They're smaller than the carbon dioxide bubbles, but they are still stable. The last thing I'll mention before I answer the question is that all these bubbles will eventually pop and burst and go away, regardless of whether you put your finger in them or not. And that's because the thin liquid layers eventually drain back into the liquid itself and the gas goes off into the air. It's just a matter of how quickly that happens. So to finally answer the question, when you put your finger, or maybe you rub your nose and you put your finger in there, the oil that's on your finger is disrupting the thin liquid layers. The smaller bubbles are breaking up into larger bubbles and then going away in that nitrogen one. And then here you can see the larger bubbles are just going away. It's not actually a chemical reaction, it's a physical phenomenon because there's no new molecules being created. There's no chemistry happening. There are situations, however, where bubbles result in chemical reactions. For example, you can use ozone bubbles to clean petroleum out of water after an oil spill. So I hope that was educational. Thanks, see you later.
Hi, my name is Jasmine and I'm a planetary scientist who studies meteorites. Today I'm going to answer a question about the Earth and Moon. Is the Moon moving farther away or closer to the Earth? Why is it doing that? Let's find out. To begin, let's start with the formation of the Moon. The Moon is thought to have formed when a Mars-sized planetary body named Theia collided with the early Earth around 4.5 billion years ago. This giant impact led to a debris disk around the Earth. The debris that was beyond the gravitational pull of the Earth came together or coalesced to form the Moon. At the time of the Moon's formation, the Earth's rotation rate was much faster, with a day about 5 hours long, compared to our current day of 24 hours. During this time, the Moon was also much closer to the Earth, about 14,000 miles away. Today, the Moon is 250,000 miles away from Earth. The Moon is still moving away from Earth at a rate of 1.48 inches per year, about the same rate at which our fingernails grow. The reason for the Moon moving away from the Earth, as well as the slower rotation of the Earth, is related to tides. Although smaller, the Moon exerts a gravitational pull on the Earth and its oceans. The Moon's gravitational attraction causes two tidal bulges in the Earth's ocean water, one on the closest side to the Moon and one on the farthest side. These both result in high tides. Low tides form at the antipode of these bulges, where the ocean level is lowest. The tidal bulge closer to the Moon, where it has its strongest gravitational pull, is because the Moon is pulling the ocean away from the Earth. While the Moon's gravitational pull is weaker on the farther side of the Earth, it is still pulling, and this time it is pulling more strongly on the center of the Earth than the more distant ocean, causing another bulge. As the Earth rotates, it twists the closest tidal bulge ahead of the Moon. Therefore, the closer tidal bulge is never directly under the Moon. As the Moon orbits the Earth, it pulls on the nearest tidal bulge. This both slows the Earth's rate of rotation and allows the Moon to move slightly ahead in its orbit. The reason for this is conservation of angular momentum, because as the Earth slows down, its energy is dissipated to the Moon, pushing it into a larger orbit. In this way, the Moon slowly spirals outward, increasing the distance between the Earth and the Moon. The phenomenon is similar to being on a merry-go-round and a feeling of being thrown outwards. So the answer to this question is yes. The Moon is moving farther away from the Earth because of tidal forces.